All right, cool. Let's go ahead and jump into it. Thanks for sticking around for the last talk of the conference. You never know what the turnout's going to be like, so I appreciate it. My name is Dan Mangum. I work at a company called Golioth. We make an IoT platform, and today I'm going to be talking about WebAssembly on Zephyr, but the talk is pretty expansive, so I'm going to be moving pretty quickly. We're going to start off with talking about just what WebAssembly is and how it works. Then we're going to move into kind of talking about dynamic code execution in general, when you should do it, when you shouldn't do it, what some of the alternatives are, and then round out with actually looking at a demo of running WebAssembly on Zephyr and talk about what some of the attributes of that are. So let's go ahead and jump in to kind of an introduction here with how WebAssembly works. So effectively, in any environment where you're going to be running WebAssembly, you start out with what the spec refers to as an embedder. This is basically the host environment in which a WebAssembly module or multiple WebAssembly modules are going to run. For an embedder, in order to run a WebAssembly module, you need to get a binary representation of that WebAssembly module. That could be, anything from on disk to fetched over the network. We're going to be talking about a variety of different models for accessing WebAssembly modules today. So once you get that WebAssembly module, you go through a number of steps in order to actually invoke code that is in that WebAssembly module. So those steps are broadly going through decoding, validation, and execution. And these are all core parts of what makes WebAssembly useful in some cases. So looking at decoding, this is runtime defined. So depending on what WebAssembly runtime you're actually using, the representation of a module instance, which is what we're moving towards here, is defined by the runtime, so it may look different. Frequently, it's represented as some sort of abstract syntax tree, but it doesn't necessarily have to be, and especially in more constrained environments, there may be other ways to represent it that can help with code size and things like that. Then you go through a set of validation. So you're basically taking that representation, running it through a number of specs, a number of attributes in the spec that classify it as well-defined and ensuring that it is a valid WebAssembly module. And then you move into execution. And execution is really what we care about, right? We want some functionality out of this WebAssembly module. So there's two steps to execution. You start off with instantiation and then invocation. Instantiation is exactly what it sounds like. You need to provide definitions for imports, so things that the WebAssembly module are going to access that are provided by the embedder or the host environment. You need to initialize globals and memories and things like that. And then if the WebAssembly module has a start function, just like any executable, that is typically run during instantiation. Now, there is some variability between WebAssembly runtimes as to whether that happens, which a lot of times is revolving around security, whether you want to go ahead and execute a function when you're instantiating or you want to wait for invocation. So if there's a start function, that's the time in which it runs. And then in invocation, you're basically pulling an exported function out of that WebAssembly module, and you're invoking it from the host environment. And you may pass it some arguments. And if you're going to pass it arguments or receive arguments from it, the runtime needs to validate that those arguments are valid. So it validates the number of arguments you have, the types of the arguments. And WebAssembly is a stack machine, so those get passed by putting those on the stack for the WebAssembly module instance, then invoking the exported function, and then it will push the return values onto the stack, which then you can pop off to get values out. Okay, so what is in this module that we're creating an instance of, and how are we able to kind of like communicate across boundaries from the host environment and the module instance? A WebAssembly module looks a lot like any other executable file in that it's made up of sections. There are a lot of sections here, and there's a lot of different things you can do with WebAssembly modules, which are one of the ways that allow it to be so portable. We're not going to go through all of these today. I did write a blog post if you're interested in understanding every byte in a Wasm module. You can go check that out if you have 21 minutes on your hand to look at a lot of hex dumps. But we're going to talk about three specific sections today because they're kind of relevant for how we're going to interact with a WebAssembly module. So let's start off with an example module. One of the things that's going to be kind of a common theme throughout this presentation is that a WASM module WASM can be targeted by really any language. So we're going to be using Rust as an example today, but you can obviously use other languages as well. This is a very simple module. What we're looking at here is that we have a single function defined in the WASM module. That is maybe alert. It takes a value, it compares the value to a constant value, and if it's over that value, then it's going to trigger an alert function, which is provided by the host environment. And so you can see that we're declaring the alert function, which does not take any arguments or return any values. Once again, a very simple module here, and that's going to be provided by the embedder. Typically, when we look at a compiled WASM module and we want to see what's inside of it, we'll represent it with WAT, which is the WebAssembly text representation. And so you can see some of our function body being translated to WebAssembly here, as well as things like the exports and imports and various signatures for the functions. So starting off, if we look down towards the bottom of our WebAssembly module here, we have a custom section. The custom section can provide really anything. It's runtime defined or compiler defined in this case. And so here we're just saying that this was compiled by Rust C, and the language is Rust, but it can also provide third-party extensions. One of the things that's really important when working with WebAssembly on microcontrollers is the amount of memory we're going to use, and it takes memory to be able to take this WebAssembly module, translate it and interpret it, and then execute it. There's obviously more overhead than just running native code would be. So for an example, some WebAssembly runtimes that can be run on microcontrollers will take the native code for whatever target is going to be targeted, or for multiple targets, shove that into the custom section and actually have it along with the WebAssembly module. So you could have it executed natively or interpreted depending on what environment you're in. So you preserve that portability while also improving performance in the more constrained environments. Looking at the import, that's exactly like we said. We have an alert function. You can import functions, tables, memories, globals, basically anything that you want the WebAssembly module to be able to access that's outside of its sandboxed environment. There is a namespacing mechanism for imports. So here you can see we're in the env namespace, and we are importing a function with name alert. And the function imports, which is the only kind that we have here, are going to include a signature, which basically allows the WASM module to know how to, or the WASM function that calls it, know how to invoke that function. And these must be available at instantiation, which may be obvious because we mentioned that when you start or invoke the start function, you need to have access to all of the imports. We also have the exports. So we're exporting a variety of things by default, and then we explicitly mention that we would export that maybe alert function, which is going to make that available for the embedder host environment to be able to call. So once again, functions, tables, memories, globals can be exported. And it's not a two-level namespace in export, so that was copied over. And these are available after instantiation. All right, so why do we care about these specific sections? We already mentioned the custom section and how that can be useful for constrained environments. But for imports and exports, one of the important things to think about is if you're going to put something in a sandbox environment and get some of the benefits that come with that, you're going to need to be able to communicate outside of that sandbox environment to be able to do anything of consequence. So if we're going to share primitive values across a sandbox boundary, WASM only supports very primitive types. So basically integers and floats are what you're going to be able to pass as function arguments and return values, which significantly limits what you can do. So we're going to pass those primitive values as function arguments and return them as values. And if you're going to share complex values without any other mechanisms, typically what you would do is from the host environment, you're going to write into a section of the WASM module instance memory, and then you're going to pass an address to a function in the Wasm module so it knows where to access that data in its memory space. But fortunately, lots of people have struggled with this, and it's not a great way to pass around more complex values. So there's kind of two components that are important to understand in the WebAssembly ecosystem. So the first one is WASI, or the WebAssembly System Interface. This is kind of like POSIX for WebAssembly. So you can see here the kind of summary of it, but basically it is a standard interface. So think about that alert function that we imported into the WebAssembly module. Imagine if you kind of had a set of libc functions that were basically available and you could count on those being present. That's kind of what WASI is defining for WebAssembly modules. And you'll see we get a nice call out of embedded devices in the high-level summary. The other part of that, which version 0.2 of the WebAssembly system interface is built on top of, is the component model. So you can imagine if we have lots of WebAssembly modules that are all importing and exporting different functions, it can be very hard for these to interoperate with each other. So the component module goes beyond kind of those primitive types in various different imports and exports and allows you to declare interfaces that then can be implemented essentially by various Wasm modules. This allows you to also combine WebAssembly modules that are compiled from different languages and have different APIs and that sort of thing to work together all at once. So WASI 0.2 is built on the component model. All right. So what we care about here, at least today, is WebAssembly on microcontrollers. For some background, WebAssembly, as is widely known, was primarily built to kind of replace JavaScript in a browser context, but it was an explicit goal for that to be able to run elsewhere and also be useful in those environments. So the WebAssembly specification mentions a variety of attributes or motivations for its design, and they fall into two categories: semantics and representation. So on the semantics side, we have a number. We're going to go through these individually, and we also have on the representation. But what we're kind of asking ourselves here is this better than the status quo, right? Like, why would we want to introduce more complexity into our firmware? And there's a variety of reasons we may want to do that, but it really comes down to two different categories when you're evaluating these various attributes and whether they would be useful to you. The first is you require dynamic code execution, so you have to be able to do this to accomplish a given use case. I would argue that that's probably less frequent than we might say it is that you need to do that, but there are definitely valid scenarios, but also evaluating it in the context of it not being required. I think that that significantly constrains the reason why you would want to put an interpreter in a sandbox environment onto a microcontroller, but there are some instances in which that can be useful depending on the rest of your system and what's surrounding that embedded device. So does your product require dynamic code execution? Like I said, probably not. So if you don't need to introduce more complexity, let's not add more complexity. Let's not use up more of your memory in your firmware. Carefully think about whether you want to do that. There's also alternatives if you do need dynamic code execution. So I went to a talk earlier today on Lex, and that is native to Zephyr now. And there's a lot of great capabilities there. There are some differences. I'm going to be talking more generally today, comparing kind of like against all alternatives vaguely. But if you want to get more into specifics, we can talk after, or the folks who work on that subsystem can certainly give more information than I can. All right, so starting off with some of the attributes of WebAssembly is that it strives to be fast. And so it tries to execute with near native code performance. Obviously, when you're interpreting, there is overhead compared to native code, but one of the ways that that Wasm is able to get closer to that is by modeling a lot of modern hardware function in the WebAssembly virtual ISA, if you will. So Wasm strives to be as fast or faster than JavaScript, but a lot of times we're not comparing to running JavaScript when we're talking about microcontrollers. So is Wasm going to be faster than C? Typically not, right? So if you don't need dynamic code execution, you're going to be giving up some performance likely. I will say this is less than or equal to, because there are some caveats whenever you're doing JIT and being able to get more context when you're compiling on the fly. But if we're talking about whether you need dynamic code execution, is it faster? In both cases, if you need it or not, you're probably going to be giving up some performance here. So that's a kind of penalty you get for bringing WebAssembly into the picture. When we talk about safety, WebAssembly is very interested in safety, because when you're executing code in the browser, you're primarily fetching untrusted code from all over the internet. So it's very important that you're able to sandbox that well. That may be less important on a microcontroller, because you probably aren't running third-party untrusted code, but in some cases you may be. And in that case, that isolation is useful. So like I said, it's really valuable when you're running multiple untrusted programs. But there are also memory-safe alternatives to embedded C. So I know there's been a number of talks about Rust. That's not the only memory-safe option. There are other alternatives as well, but that's just one that's obviously been popular as of late. So if you need dynamic code execution, this isolation is going to be useful. If you don't need it, there are other ways to get memory safety, and probably less complex ways as well. So grouping the next few together, well-defined, hardware independent, and language independent. If you're only going to be running code on a microcontroller, doesn't really matter too much if you're hardware and language independent. So this isn't bringing too much value for us. It is useful if you're going to be moving that between different environments or potentially onto different microcontrollers. But once again, embedded languages, if you're compiling firmware binaries, you can target different architectures. And obviously, if you have a system like Zephyr, it's really easy to move between different hardware. Another thing that's important to note is, because we're still doing, we're executing in a linear memory space for a Wasm module instance, languages that do not have direct memory access or can directly access hardware are still going to struggle in a context where that's necessary. So if we're passing pointers and offsets to functions, accessing that memory and working with it, even within a Wasm module instance context, is going to be difficult with a language like JavaScript. So if dynamic code execution is not required, these are not super useful for you. They're also not necessarily super useful for you if you do need it. You can get some of these, right, with Lex or something like that. Platform independence is something that I think is a little more interesting to think about when you view a full context of a system, of which an embedded device may be one component. Platform independence is a goal of WebAssembly, and at least at Golioth and in some of the work that I do, we think this is really interesting. So I would say the kind of killer application of WebAssembly in embedded is transferable computation. And when I'm talking about transferable computation, basically saying you can move operations between different types of heterogeneous compute depending on what your goals are and where you're trying to optimize. So this can be really useful for cases like you want to manipulate data at different points of the process of that data getting from an embedded device to ultimately being in a data store. It can be useful for making data-driven decisions, which is something we're going to be looking at a demo for today. And it can be useful when you're prototyping or experimenting. If you're going to have static behavior that's not changing that much, once again, having dynamic code execution is not going to be super useful to you. But in both these cases, platform independence can be useful. Open, I'm mostly going to skip over this. I'm going to assume here at the Zephyr Developer Summit that we're all interested in open, and many alternatives are open. So we're not really getting too much of an advantage by WebAssembly being open, but it's great that it is. All right, looking at the representation, I'll move a little faster on this. A bunch of these are not taking into account the fact that you have to have a runtime present in the environment. So if you're in a browser, right, that's not too big of a deal. If you're on a microcontroller, that may be the most significant use of memory on your device. So that's obviously going to be an issue. Also, if you're just thinking about being able to minimize the size of the code that you're getting down on a device. There are other ways to do that, and they're going to pretty much always be more efficient than having a interpreter you need to put on the device and then fetching a module to run on that interpreter. And a lot of times raw speed is also not our most important attribute, and you may be willing to trade that off for things like conserving power or being able to go to sleep more often, that sort of thing. So once again, WebAssembly not giving us a lot of advantage there in a vacuum. But portability is kind of related to the platform independence. And so the portable representation that WebAssembly gives us is really, at least for today, with what we're concerned about, the most valuable attribute of Wasm in this context. All right, so if we look at a system where we're using WebAssembly across heterogeneous compute, we think about that a lot at Golioth, and what that may look like is having a lot of devices on one side and then some type of middleware in the middle that is getting that data off the device into a cloud somewhere else or to a consumer application somewhere else. So we like to talk about the device side and the cloud side, and then having middleware in the middle where you can optimize that data, you can transform that data, and then you can ultimately deliver it to where you want to use it and consume it. And this is bidirectional, right? This could be going from your backend or from your cloud down to devices or vice versa. Today we're going to be looking primarily at data flowing from devices to your cloud. So why might you want to run WebAssembly at kind of each stage in the system here? Well, if you want to run it on something like Golioth, you're probably going to have a runtime provided for you. You're not under the constraints that you would have on a device, so having a runtime present is not something that's much of a concern. And you can provide optimization by perhaps filtering data or compressing it or something like that before it ends up on your cloud backend. You might want to run it on your cloud backend to have full control of how you're executing code. You might actually want to get, if you're building a product on top of a system like this, you might want to get WASM modules or code written by your customer to be able to run it against data in your backend, or take action on data, such as alerting, which is a example that we're going to look at today. And then you might want to do it on your device. We have a lot of customers and users who have cellular devices, and obviously when you're using cellular, you're concerned about bandwidth. So if you want to maybe reduce the amount of data that is sent over a cellular network, this could be a useful way to get some optimization there that may also be able to run in other environments. Okay, so getting to the title of the talk, we're going to look at WebAssembly on Zephyr, and I'm going to give a brief overview of one runtime that's kind of, in my approximation, really the most popular for embedded devices right now, and then we're going to jump into some code and look at how that actually works. So WebAssembly Micro Runtime, or WAMR, if you've been to other talks this week, it's come up a few times. This is under the Bytecode Alliance, which is where lots of the WebAssembly work happens. It's optimized for constrained environments. It's kind of in the name there. So the interpreter runtime size is about 85 kilobytes, which is not insignificant, but if you compare it to other runtimes, pretty incredible. It supports multiple execution models. So regular interpreted WebAssembly that we're familiar with, just-in-time compilation, and then what I mentioned earlier was ahead of time. So that's essentially where they have a compiler that they offer that allows you to take a WebAssembly module, compile it for the target, and then deliver that either in the custom section, which is what some runtimes do. WAMR, or WebAssembly Micro Runtime, actually has a different file format for that ahead of time compilation. And that's going to bring down your runtime size quite a bit if you're using native code. It also implements execute in place, which is extremely useful and is not something that's represented or implemented by all alternatives. So that's a really nice attribute that's available to you with WAMR. It also includes a Zephyr port, which is how I'm able to give you a demo today. And it's pretty close to being able to just be pulled in as a Zephyr module. And lastly, it supports WASI. This is not super useful today in the embedded ecosystem, but there's a lot of work that's happening in WASI to be able to expose things like SPI or I2C as standard interfaces. And so that's going to make this a lot more useful and also give you kind of a API to program against when you're writing WebAssembly modules that are intended to run in that environment. All right, so I'm going to stop talking up here at you with slides, and we're actually just going to look at implementing it. So in the demo that I'm going to give today, we're going to create a WebAssembly module that looks a lot like what we have in our example here, and we are going to run that kind of on either side of Golioth, the platform in the middle there, and we're going to use that to alert on temperature values. So starting off, here's the, if I jump out of here into the source, here is our example module that we looked at, where we can pass, in this case, it's going to be the temperature, and we're going to say if it's over 22 degrees, we're going to call that alert function. So I've already compiled this, but I'll go through the steps again, and we'll build it. So that goes pretty quick, and I am going to take this output, and we are going to base64 encode it. Let's see, simple WASM. And I'm going to use our setting service to basically put this onto a device here, which I'm going to start up in just a moment. So this is the console that we have, and I'm going to go in and change our existing WebAssembly module here. And we're not used to settings this large usually, but I'm going to go ahead and start up my device running here as well, which is an NRF 52840 development kit with an ESP32 for Wi-Fi. So that's going to start up, and we should see it connect here. And essentially what it's going to do is boot up, connect to this Wi-Fi network. It's going to fetch that WebAssembly module and then start going through a loop. And we're going to look at the actual code that it's executing. I'm also going to make this a little bit bigger here for y'all. Let me just go across and make sure. Is that big enough? Bigger? Good? All right, cool. So we can see here that we are streaming some temperature values, and then we have a alert that's happening for some of them, actually for all of them, which we're going to see. Any of them that are over 22, we should see an alert happening here. So this is the firmware that's running on the device. So up at the top, we have our alert function. So this is what we are going to import to our WebAssembly module that it can invoke. So in this case, all it's doing is saying whenever I get invoked, I log a message that says alert, and you could do something like blink a light or whatever you wanted in the context of your device. I'm going to go down to main here and see how we start up. First thing you're going to do with WebAssembly micro runtime is go ahead and instantiate or init the runtime. And there's a variety of settings you can provide there. One that we're going to provide is the native symbols, so the symbols to be imported to any module that we want to run. We're going to define how we want to allocate memory and a variety of other settings, and then initialize the runtime. And then loading the WASM module, I have one by default in this firmware binary that's just the bytes that it's going to load, and then it's going to start up and connect to Golioth, which is what we're doing here. Creates a co-op connection over DTLS, which is how we're able to fetch those settings and then stream our temperature data up to Golioth. We're also registering our setting there, which creates an observation. So anytime we update the content of our WebAssembly module, that is going to be observed by the device, pulled down, and then it's going to start invoking the new one instead. So our loop here is pretty simple. It's just looping through 5 values here and simulating like reading temperature, streaming it up to Golioth, and then invoking the Wasm module with whatever value it just streamed up. So that's great, but like I said, we also want to show this happening on the other side. So I'm going to start up a HTTP server here just locally, and what this is going to do is connect to Golioth over WebSocket and basically receive all of those streamed values that are coming from the device. And you're seeing here that I'm getting some alerts because it's also fetching that same Wasm module and running it in what we could view here as the client application. So we're being able to use that consistent logic in two very different environments, right? A microcontroller and our browser here. And we might want to go in and change this over time. Obviously, this is a simple example where the value could just be, we're gonna stop this for just a second so that I can keep doing this demo. This is a simple example where the value could be represented by a setting or something like that, but maybe you don't want to alert when you're calling it. I also wanted to show a bit of what's happening behind the scenes here in that simple web page. We're connecting, as I said, to Golioth to stream those values. And the important part here is that our alert function is calling a browser API instead of a device log message. But to the Wasm module, right, it's programming against the interface that we've given it, which is just an alert function that takes no values and returns no values. Once again, a simple example, but it shows how, depending on where it's executing, the embedder can provide different functionality to it. So let's go ahead and change that and show the device picking it up. So I'm going to pick a value that's kind of in the middle of some of those temperatures. We'll say 65. I'm going to go ahead and recompile that, get the base 64 for it, and copy it up. That's not what we want. All right. So we'll change this to our new Wasm module, and we should see that when we update that on the device, we have a new Wasm module coming through here, and I'm going to restart this shortly because it looks like we had it recovered. Here we're seeing that we have a streaming temp, and when we invoke the Wasm module, it's no longer alerting because it's under the value. And actually, yeah, I'm going to go ahead and restart this because I think it lost connection. But when it comes back up, we'll start iterating through those values, and we've changed the behavior so that it has a different response based on the value that's passed to it. And we can do the same on the web server side, pulling that in, 8,000 alert. And we should see temperature values start to stream through here as well. That first one was over 65, but all of them that are under are going to come through without our alerting logic. So we just see 48 come in under 65. So yeah, that's kind of an example of running a WebAssembly module in two very different contexts, but being able to provide different functionality in each. So with that, I'll open it up to any questions.
Thank you. So in that demo, was that an example of just-in-time compilation or ahead-of-time compilation?
It was actually neither. It was just interpreted.
Okay.
So, yeah.
So in the just-in-time case, what exactly is the input and output of that compilation?
Yeah. So in the just-in-time case, the input is just going to be the Wasm module binary, and it will get compiled to native code on the fly on the device. And so, that can improve performance in some cases, especially if you're in kind of a tight loop there.
Thanks.
Hey, great talk. Couple couple questions for you. How big was the end WASM file that you had there that you had to pull over? It looked pretty small, base64 encoded.
Yeah, I think it was 452 bytes.
That's pretty nice. And then I guess like, have you done any comparison with, like you write a C function that does some tight loop with math, you do a WASM function that does some tight loop with math, kind of like maybe a digital filter might, and compare and contrast kind of the performance difference?
Yeah, I haven't run any benchmarks. There are some in the WAMR repo, I believe, that some folks have done. But no, I haven't performed any myself.
Okay. Thank you.
We do have some online questions. So I think this is referring to the slide where you were showing the WASM running in all the different places.
Mm-hmm.
So the question is this like a combo of remote proc and WASM, i.e. push WASM code blobs to another processor core to run on the other side, or via networks, Wi-Fi, SPI, I2C, etc.? Are you aiming for that?
Can you say the beginning of that again?
Is this like a combo of remote proc and WASM? Remote pros? Remote
okay.
PRIC?
Yeah. I guess sort of. That wasn't an explicit goal of the what I was demonstrating here. One of the things that I do think is interesting, if you're using WASI and you have you leverage access to a SPI bus or something like that, is that's going to reduce some of the portability, unless if you're able to simulate that in a browser environment or something like that. So it's not all translatable. There's portability is going to depend on what you're able to provide in each environment. So kind of the more you expand that interface you're programming against, the harder that may become.
Another one here. As WebAssembly continues to gain traction, how might it reshape the landscape of web development, and what opportunities does it present for developers, businesses, and the broader tech ecosystem?
That is sounds like it was from a corporate briefing, but I don't know how this is going to affect the life of web developers. I know that it's used in some performance critical web applications, and it's been useful in that context. I think that being able to run code against various different environments is useful. I will say that like one critique of this, and obviously I'm coming at this working at a platform company, is this really providing value to end users, or is this providing more value to the platform? And I think that's a fair question. Obviously, it's useful for us, for example, to be able to run code in a nice sandbox, but is that imposing more burden onto developers to have to learn WebAssembly and implement it and that sort of thing? I think it's a fair question to have.
Any more questions in the room?
Yeah, how would you go about, I mean, there's always bugs, even if you write it in Rust code, there's always going to be bugs. So how would you debug WASI on your device? Should it go ahead and blow up?
Sorry, can you say the end of that again?
Yeah, how would you go about debugging your WASM module on device? Should it fail?
Yeah, it's going to be more complex when you introduce an interpreter. So I think that's maybe something that wasn't referenced in the attributes, but something that's definitely a downside of bringing a runtime into your firmware. There are there's some efforts in WAMR, I know, to make debugging a little bit easier. I think that's specifically focused on debugging the runtime. One of the ways that you can do that is you can pull exceptions out of the WebAssembly sandbox and view them in embedder. But in terms of stepping through code in the interpreter, that's going to be a lot harder, and it's probably going to be dependent on the runtime providing you some hooks to be able to do that. So I would say it's a negative experience today.
Yeah. Thank you.
Curious if you've seen or looked at any comparisons kind of from a footprint size on like this versus MicroPython, or I know there was some Lua JIT or Lua work that was talked about a couple years ago with Zephyr.
Yeah, I haven't done any comparisons myself. I've read some online, but I think it's pretty use case dependent. So I wouldn't speak to any specific comparisons, but there are some available. Cool.
Any last questions?
Great. Thank you all for coming, and I hope everyone has a safe flight back.